clearly describe, again, the decimal behavior of a rational number. The decimal behavior of a rational number is it's going to T or R. It's going to terminate or it's going to repeat, one or the other. Okay? Clearly describe the decimal behavior of an irrational number. Never T's, never R's, goes on forever. In other words, it never ends. It can have numbers all over the place, or it can have patterns in it which grow. The pattern has to grow in order for it to be considered to be an irrational number. If the pattern didn't grow, it would be like a repeating decimal, and of course that's not the situation. So you've learned about the Kelly's-Teeter method. So let's take a few minutes and review some of that material involving the Kelly's-Teeter method. So let's take a look at this particular sheet. You don't have this, but I do. And let's take a look at these problems. If you'd like to write them down as I do them, you may certainly do that. But let's take a look and see if we can remember what the important points were you were to have learned about the Kelly's-Teeter method. All right, first of all, it says, convert the following decimals back into the fractions they came from using the Kelly's-Teeter method where applicable. Indicate why any particular decimal shown cannot be converted by any method back into a fraction. So let's take a look at the first one, 92.36, or 92 and 36/100ths. Can we convert that back to the fraction it came from? Well, as you know, this particular whole number, 92, can be written this way, and I don't need that decimal point, so I shouldn't have really put it there. Pretend it's not there. And what do I do with 36/100ths? Well, it's not a repeater, right? So I can simply, to convert it, I simply have to, since it terminates, put it over its place value, 36/100. And now if I want to reduce 36/100ths, I most certainly can do that, all right? But I'm not requiring you to do that. It turns out, I believe it's 9/25ths, but you do not have to reduce it. So there's the answer for that one. What do we do in the case of 92.36 with the bar over the 3 and 6? Now, of course, they are repeating. And if you recall, by the Kelly's-Teeter method, you simply, once again, write down your 92, okay, the whole number part, but the 36 repeats with 2 digits, doesn't it? Okay, so how many 9s do we put 36 over? Well, since it's repeating with 2 digits, I simply put it over 99 and I am finished. That simple. Let's look at the next one. -4, I'm going to have to put down first, right? It repeats, the 375 repeats in 3 digits, right? So I will put 375 over how many 9s? Well, as you recall, you put it over 3 9s. Now, let me just say this. You probably can reduce this fraction, but I'm not requiring you to do that, so don't worry about it. All right? Now, look at this next one. Crazy, huh? It repeats over 6 digits. So guess what? As far as the Kelly-Teeter method has told you, you can do what? You put those 6 digits, 8, 5, 7, 1, 4, 2, over how many 9s? You're right, it's 6 9s. If you want a bit of a challenge, reduce that fraction and see what it reduces to. It reduces to a very simple fraction, and I'll give you a hint. Its denominator is 7, okay? The sevenths are 6-digit repeaters. So see if you can figure out where that came from. In the next one, it's a 4-digit repeater. The 3633 repeats again, and then again, and then again. So what you do, if you recall, is you put your 24 whole number down, okay? And the 3633 goes over how many nines? It goes over 4 nines, right? And I'm sure that this will reduce. You can see that both the top and bottom are divisible by 3, but again, you do not, for me, have to reduce that fraction to lowest terms. How about the next one? What's the story there? Is that a repeating decimal? No, it's not. And as you recall, it's a decimal which is growing in size, showing a pattern. It started with 2, 3, then 2, 3, 3, then 2 and 3 threes, and 2 then and 4 threes. So you can assume because of the dot, dot, dot notation that it continues to go on forever, right? And the pattern will continue to increase in size. So we cannot use the Kelly's cheater method to convert this. And why is that? The reason is this number right here is irrational. Irrational numbers can never be expressed as fractions. Remember, the Greeks thought that all numbers could be expressed as fractions, but they found out, of course, as you've seen in some of the earlier videos, that ain't the case, right? And if you recall from high school, radical 3, radical 5, pi, some of these other crazy numbers that go on forever are irrational, and they cannot be written as fractions. So there, we've done a very quick review of the idea of the Kelly's cheater method and some cases where you cannot use it. All right, let's continue on and return to going over the homework. Let's take a quick look at the back of this sheet. Remember, I keep hitting you with this because it's going to be on the next test, and I want you to make sure that you know how to do this. To get a rational number between 738.020305 and 020308, you need to take those two numbers, add them together, and divide them by 2. When you have done that, you will get this number, which is exactly halfway between them. Am I finished with this problem? As a matter of fact, I am, right? Because that's a rational number, it terminates, okay? Now, I could have put a bar over the 6 and 5, and it'd be 6, 5, 6, 5, 6, 5 forever. That still would be between them. You just have to make sure, if it's a rational number, that the number is really between the two numbers in question, okay? All right, let's go to the next one. We want an irrational number between these guys, all right? So let's see. If I divide those two, add them together and divide by 2, I would get this. There's a 0 I could put there, a 0 I could put there without changing the value of the original numbers. That number is right between them, but it's rational. I have 3 choices that I can do to show that this is an irrational number. Add a whole bunch of numbers to it, like 3, 1, 8, 6, 5, 9, 2, dot, dot, dot. And simply, I will realize that you mean an irrational number because the numbers are all over the place, okay? That's one way. What's another way I could do this? Another way I could do this is to do what? I could simply put an arrow after it. The arrow would say, and I could put some numbers before the arrow if I wanted. That arrow is a Kellyism, but it tells me you know what you're doing and that you understand that the numbers continue and go all over the place. You don't put 3 dots because the 3 dots would mean in the same pattern. And, I wouldn't know what you mean there. All right. But that's not my favorite way, right? My favorite way to have you do this is to stick a pattern on here. Now, you've got the 6, 5 there, right? But I'm going to use a different number. I'm going to use 3 numbers, 1, 2, 3. Okay? So I'm going to put 1, whoop, I got to get the pen turned on here. I'm going to do 1, 2, 3, 1, 1, 2, 3, 1, 1, 1, 2, 3. I'm going to come down here and keep going. 1, 1, 1, 1, 2, 3, dot, dot, dot. That is definitely an irrational number showing a growing pattern. And that is acceptable. But that answer would be wrong if you forget to put the 3 dots after it. The 3 dots tell you that it continues in the same pattern. Don't forget the 3 dots if you elect to show your answer in that method. Okay, what else is on here? Well, there's a credit card problem on here. We're not doing credit cards, right? But you, I'm sure by now, are very familiar with UPC codes, okay? So, of course, I would want you to multiply everything by 31313131. Maybe we should do it real quick just to make sure you're comfortable with it. I multiply everything out. This is a fairly simple one because there's a lot of zeros in it. And it turns out there are no 2-digit numbers in here. So this makes it pretty simple. All right, so I add these up. 13 and 4 are 17, 18. Hopefully I'll have better luck this time. 18 and 3 is 21, 24. So 3x plus 24 has to come out equal to 0 mod 10, right? So what am I going to do here? Well, I'm looking for a number that produces a digit on the end so that when I add it to 24, it ends in 0, right? Well, it appears I'm going to need a 6, right? What number do I need for x to have the number 3x end in a 6? Well, it turns out it's just going to be x equals what? 2. 2 times 3 is 6. It certainly ends in a 6. 6 and 24 adds up to 30, so you know we're good. X has to be equal to 2 for this code for Jell-O chocolate vanilla swirls to be shown correctly with the right type of UPC code. Okay? Now, with this all being said and done today, what is it that I want you to do, all right, for homework after this particular video? Okay, I'm going to ask you to do the following. I'm going to ask you to do group work number 13. There's only a few parts to that, okay? And I would like you also to do just a few parts that I haven't crossed out on group work number 16. I would also like you to complete video quiz number 13. Just text me the answers only to video quiz 13. Take your time and do a good job on that, okay? I don't want you to mess that up, okay? Might as well get that 10 points, all right? What if I tell you you are only allowed to use 9s and 5s to make these kind of numbers, okay? I would like you to make me 3 rational numbers, 3 of them, which have only 9s and 5s in them. Well, let's see. 5/9 only has 5 and 9s in them. 0.95 bar is a rational number that repeats with only 9s and 5s. Okay? 9/5 it also is going to be a decimal. Okay? And that decimal, I believe, comes out 1 point. I'm not even sure. Let me divide it out and see. 5 goes in there once with 4 left over. 4/5 is 0.8. So this is just 1.8, but I can't use 1.8 in that form. I want this form with only 9s and 5s. I could use 59.9559, 9559, 9559 with 3 dots after it. That is, of course, a rational number which is showing repetition, but not with bar notation. In bar notation, it would look like this, right? I would like you to write for me 3 irrational numbers with just 5s or 9s in them. All right? Well, one of them could be like this. 5.95955. There's an infinite number of answers you could write for this, okay, that I would accept. So I have to look at everybody's answers to make sure I am pleased with what you have written and that it is correct. I'm putting a pattern on here, right? I didn't do it right. I need 3 5s there. I need 4 5s here. Dot, dot, dot. So there's one. Let's come up with another one that's irrational. These are the irrational ones, right? Okay, what else would work? Well, I'd have to use some kind of combinations with 5s and 9s, right? So I could do 9.95, 995, 9995, 9999, 5 dot, dot, dot. There's another irrational number with that. I could use 5, right? And then I could use what? 3 9s and a 5. 4 9s. Well, I've already done kind of that. So let's do 3 9s and a 5, 3 9s and 2 5s, 3 9s and 3 5s, dot, dot, dot. All of these three examples right here all show growing patterns, don't they? And growing patterns, like what I'm showing right there, work very well in terms of producing for you an irrational number. Well, with our next major test on the horizon, I think we should take a few minutes and do a review sheet once again to help us get ready for this next major quiz, Big Quiz 2. The sheet I'm going to work on is called GroupWork 16 Review. I did send it to you, and hopefully you have yourself set up so that you can write on it as we do this together. So hopefully you're watching me on one video screen and you have your computer ready to go. As a PDF, you have the file ready to write on as we go through this. So I'm going to go through this stuff rather quickly, but slow enough that hopefully you can get a good idea to make sure that you understand what we're doing. So with no further ado, let's get started. All right, I'm going to start with the first problem. Are these statements correct? Are they true or false? And we're going to determine whether or not they're true or false by obviously working them out. The simplest thing to do in problem number 1, the first one, the mod 8 problem, is to take the problem and just work it out on the left side. And once we've worked it out on the left side, convert it to mod 8. I should really have different symbols in here instead of equal signs. They should be identical signs, but that's all right. We'll let that slide. So at any rate, here we go. So what I'm going to do first on my calculator is I'm going to multiply 17 times 38. Hopefully you have a calculator handy and you're doing all this with me. So we should be looking at 646. All right. And from it, we will subtract 5 to the third power. I'm sure that 5 to the third power is 125, but I'm just checking it out. So 125. And now that I have those written down, I want to figure out what that is, obviously. So I do 646. All right, it would help if I did this correctly. 646 minus 125, and that gives me 521. So I'll put the 521 down, and now I want to convert that to mod 8. So we want to know what it is mod 8. We need to take 521 and divide it by the mod number we're trying to convert to, which is 8. So if you take your calculator right now and divide 521 by 8, you will notice it does not come out even. It goes in 65 times with a decimal which goes on. So what I'm going to do is I'm going to take the whole number 65 and I'm going to multiply 65 times 8. And when I do, I get 520. So I'm putting the 520 down here. And what I simply do is subtract. And as you recall, the remainder is the answer in mod 8. So the answer is 1. So this is equivalent to 1 mod 8, not 7 mod 8. So this statement is false. A lot of people, when they take this test that I'm going to give you, they take a problem like this and they stop when they get the 521. And they say the statement is false, but they don't show why 521 is false. Remember, you have to make sure that you turn it into the mod number that it's suggesting. In this case, it was mod 8. So let's make sure you do that when you take the test. The test is coming up in a while. It's not going to be for a few days yet, so don't worry. All right, let's go to the second example underneath number 1. 529 times 46 plus 832, is that equivalent to 6 mod 10? Oh, wait, this is in mod 10, so it's a very simple problem. 529 I can change right away to mod 10. It's just 9. 46 is just 6. 6 times 9 is 54. So this first part of the problem is just a 4. I'm going to add to that 832. Well, 832 is just what? 2 mod 10, right? So this is plus 2, just plus 2 down here. So I get 6. And, of course, the answer is 6 mod 10 that I'm suggesting. So this statement is definitely true. Okay, any question on that? Hopefully not. All right, so if they're mod 10s, they're pretty simple, but life isn't always that simple, as we know. All right, let's go to the next question. Write an example of an irrational number made up of only 7s and 9s. Now remember, if it's an irrational number, it has to go on forever as a decimal. It never stops. And we can't use my arrow method to show that it goes on forever because we'd have numbers other than 7s and 9s probably in there, right? So I'm going to start here with 79. That's not irrational, obviously, but I'm going to write down next 79. Now, what would be the easiest way for me to make an irrational number here that we know will go on forever but never repeat. And it'll have only 7s and 9s in it. Well, if you recall, the simplest thing to do here is to do a pattern that has 7s and 9s in it, but a pattern that continuously increases. All right? So if we do 7, 9, how about if I do 7, 7, 9 next? And then 7, 7, 7, 9. And then 7, 7, 7, 7, 9. I can even do one more. Notice I'm going up to 5 7s. Now, how do I show the reader that this number goes on forever and still is irrational? Well, I do have to put the 3 dots there. The 3 dots say continues in the same pattern, right? And because we can see that the pattern is increasing to infinity, we know the 7s will just keep increasing, one right after the other, 6 of them, 7 of them, 8 of them, 9 of them, and so forth, all the way to infinity. So therefore, I have written the answer correctly for this. Is this the only answer that would work? No, it is not. I just happened to pick using 7s and 9s. You could have used 79, and then you could have gone 997, or excuse me, 97, 997, 9997. You can make up your own. When I grade this test, I have to look at your answers carefully to make sure you've answered the question correctly. Okay? So feel free to realize that there's going to be, this is not the only answer, there's going to be a lot of answers that are going to work. All right, let's go on to number 3. Write an example of a rational number made up of only 4s and 3s. Well, I could do this. I could make one example be 3/4. That is a rational number. It has in it only 3s and 4s. Even though when I convert it, it's not going to be just 3s and 4s. But as it stands right now, that is a rational number which has in it only a 3 and a 4. Okay? I could have used 4/3. Now, what if I instead had decided to make a decimal number with only 4s and 3s in it? Okay, it's still rational. That means it's either got to terminate. So I could do 43.34, all right? Or I could make it repeat. I could do 43.34 bar, okay? Or I could have done 4.3 bar. There's all kinds of potential answers here that will work. All I have to remember is that I must use either a fraction, which has only the numbers in it, a decimal which terminates with only 4s and 3s, or a decimal which repeats with either 4s or 3s in it. And I cannot have a growing pattern. A growing pattern decimal, okay, would be irrational once I put the dots on it. Of course, I didn't put any dots here. I could have written these using ... notation. This is unusual to only show 1 3, so you probably would never do that. But you could do this, show a few 3s, and then show that the pattern continues to infinity. All right, so there are some examples of how to answer questions 2 and 3. And obviously those will be on the next test. If you're having trouble with those, you should text me and let me know. Maybe we can do a quick Zoom meeting to help you understand this concept a little better, okay? All right, let's go on. Assume a particular culture uses a mod 11 clock to tell time. Soon the clock shows the numbers 0 through 10 on its face. If the clock now reads 8, what time will it read in 58 hours from now? I could actually make this mod 8 clock, put a circle down, put the digits 0 through 10 on it, and put an arrow out to the time 8 and count ahead 58 hours. That's too much work. I got to count and all that stuff. The simplest thing to do, if you recall, is to simply do this. Simply take the time it is, 8 o'clock, and add to it the number of hours, 58. That gives us what? 66 o'clock. Now, how do I convert 66 into a mod 11 number? Well, I divide 11, excuse me, I've said that wrong. Let's start that again. I take 66 and I divide it by its mod number 11. All right? It goes exactly 6 times, right? So what time is it? The time is 0. So our hand would point to the 0 on the clock. When you encounter this question on the test that will be coming up, you want to make sure you show all these steps, or else draw the clock face and show that you've counted around until you get to the correct answer. Okay, let's go on. Let's go to question 5. Let's convert each of the following decimals back into the fractions they came from. Use the Kelly's-Teeter method where it applies, where you can use it. If the conversion cannot be accomplished, state why it can't be done. All right, well, if you look at the first example, negative 32.79, that is not a repeating decimal, is it? So I can't use the Kelly's-Teeter method at all on that one. All I really need to do this is simply take the negative 32 and, of course, write it down. And then I take the decimal portion, since it terminates, and just put it over its place value. And, of course, 2 decimal places is hundredths. So the correct answer is 32 and 79 hundredths. Okay? Look at the second example, negative 86.937 bar. Well, of course, I can simply take the negative 86, and write it down. I can put the numerator as 937. And if you recall, since this is a repeating decimal, it begins its repetition at the decimal point. So I'm allowed to use the Kelly's-Teeter method. And how many digits are repeating? 3. So I simply put this over 999 and I'm finished. Not bad. Simple. All right, the next one. 486, I'll write the whole number down first. It does satisfy the Kelly's-Teeter method, the decimal that's shown here, because it starts repeating right from the decimal point on. There are 4 digits repeating. So I simply do 3159 as the numerator, and I put it over 4 9s, and I'm finished with that one. Now, if we look at the next example, 4.323232 ... you'll notice that it's not using bar notation, but it is using repetition notation, the ... symbols, to show it goes on forever, the 3232. So you can see it's 2 digits that are repeating. So it'll simply be 4 and 32 over 99. So that one's finished. Now, how about the last example? Notice the decimal goes the decimal part goes 0.93, 933, 933s, 943s, 953s, and there are 3 dots, which are suggesting that we have a growing pattern here that goes on forever to infinity. Because of that, we realize that this is an irrational number. And you recall the definition of a rational number is any number that can be expressed as the quotient or division of two integers. You know, irrational numbers cannot be written that way. They cannot come from fractions. Therefore, this one cannot be done. So, no, we cannot do this. We cannot make that conversion. Okay, let's go to problem number 6. Determine an irrational number that is between each pair of numbers. All right, so let's take a look at 59.38 and 59.39. Well, if you take a calculator and you add those two numbers together and divide by 2, I suggest you do that right now. When you do that, you should find out that your answer would simply come out what? 59.385. Get my decimal point in here. Let me make my 8 a little better here. Now, that definitely is between those numbers. Now, the question is, we've got to make this irrational. We have 3 ways we can really do this that I would accept as a test question answer. One way would be to just start putting numbers down here. 2, 1, 3, 8, 6, 5, 9, 2, 1, 7, 9, 3, and put 3 dots after it. You can see from what I've written down that these numbers are all over the place. There is no pattern there. There doesn't appear to be any repetition there. So I could outright the fact that that number you feel is irrational, and I think probably you're absolutely correct. So that certainly works. That is one way you could write the answer. Now let me get rid of all these, and let me show you another way I could write the answer. Let's do this. What can I put behind this that would make it really easy? I would allow you to show an arrow here. Remember, that's a Kellyism. No other math teacher teaches that way, teaches this concept. If you put an arrow in my class after a decimal like that, you are telling me you know that Kellyism is saying what? It is saying this number continues to infinity, and it is all over the place. You can't use that in anybody else's math class because they don't teach that, all right? But I do, and I would accept it. So I'm going to erase that. All right, now, what else could I do? What's my favorite way? My favorite way is to show a pattern. 385, well, let's see. I don't have to use all 3 digits, but maybe just for the heck of it, I'll use all 3 for a change. 3, 8, 5, 5. I'm not expanding the 3 and 8 at all, but I am the 5, 5. Then I could go 3, 8, 5, 5, 5. And then 3, 8, 4 5s. Now I've shown enough of a pattern here so that I could simply show dot, 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 and I am finished. I have done the job. So I have come up with an irrational number which shows a growing pattern, and as a result of that, that is a correct answer for an irrational number between those two. Okay, now, so that I have room for the next problem, I'm going to take some of this off of here. So I'll reaffix the 3 dots here, all right, after this, so that it's correct in the format it's showing. All right, determine an irrational number between these two. Well, if you simply take those two numbers, 727.425, all right, And if I add to it 727.428 and divide by 2, I obtain 727.4265. Now, you know that this number is not irrational. It is what? It is rational. So we must make it irrational. So again, you can use the arrow after it, okay? So if you draw an arrow that tells me this number is going to go on forever to infinity, all over the place with numbers, I would accept that. So you know that's acceptable. If you place numbers on there yourself, which are all over the place, such as 2, 3, 8, 6, 1, 5, 9, 7, 4, and you put 3 dots, I will also accept that answer because it appears, the way the number is shown to me, that the numbers are all over the place. And of course, I would accept that. Okay? Now, also, let me show you this. Okay? I also would allow my favorite way, which is to show a pattern. So since I have 6, 5 on there, I am just going to use the 6, 5 to make the pattern. So I'm going to do 6, 5. I'm going to do 6, 6, 5, 3 6s and a 5, 4 6s and a 5, and dot, dot, dot. And of course, that suffices it as well. So any of those 3 types of answers take care of what it was we were looking for. All right, we haven't visited this maybe in a while, so let's take a quick look at this. Determine the missing digit in this UPC code. So let's do that. Let me slide this down a little bit. For Reese's peanut butter snack size cups. Oh yeah, okay. All right, so remember to do this, we need to put down here the code 313131. So I'm going to do that right now. Underneath. And of course, I have to multiply by these. Draw myself a sad line here. All right, 0, 3, 3x. I'm going to circle that. 0, 0, 0, 12, which becomes what? A 2, 0, 6, 1, 3, and 3. Now, if I add all those together, all right, and put them with the 3x plus, all right, 3 and 3 is 6, 7, 13, 14, 15, and 3 appears to be 18. All right, this has to equal 0 mod 10. So what do I need to add to 18? What number, what does it have to end in when I add it to 18 to make this become a 0? Okay, well, as it turns out, I need a what? I need a 2 on the end, right, to make 18 become 20, which would be 0. So what number times 3 gives me the 2 on the end? Of course, it's 4, right? So since 3 times 4 is equal to 12, all right, 12 and 18 would be 30. X here must equal 4. Oh, I see in my next question I'm about to ask you that I have an error. It says write a formal definition of a ration number and then clearly describe the decimal behavior of such numbers when they are converted into their decimal equivalents. Well, this should say rational. All right, there should be a T on the end there. Whatever. So, excuse me, should be ration AL, sorry, Duh. All right. So obviously I screwed that up, but at any rate, let's keep going. So what's the definition? It is simply this. Don't forget this. It's any number that can be expressed as the quotient division of two integers in the form a over b, and b cannot equal 0. Now, what is their decimal behavior? We know their decimal behavior has to be what? They either repeat as decimals or they terminate. If you put R or T down on your test, I will count that right for you explaining to me that they repeat or they terminate. Excellent. All right. Sorry about my mess up on rational up there. Confusing enough as it is sometimes, right? All right, circle each number which is an example of the kind stated at the beginning of each row. All right, I would like you to do this right now. Circle every number here that you feel is an integer. Now, I think you're probably done already. So I'm going to circle them. Here we go. We have 8. We have 82. We have 829. And we have 2,569,000, 873. Those are all integers, okay? But wait a minute, I left one out, right? Integers can also be negative, can't they? So guess what? This is also an integer, okay? Integers cannot have decimal or fraction parts, okay? Next, circle the rational numbers. Okay, well, it appears that this one is rational. It's a fraction, right? This one is a fraction, okay? And because it's a terminating decimal, I also probably wanted a repeating decimal in here. It appears my bar didn't get drawn correctly over there, but we won't worry about it. The way it looks right now, it's a terminating decimal. And this is a terminating decimal, so it is also a rational number. Repeating decimals are also rational numbers. For example, if you look at the next question, 58.62 is an example of a rational number. But it said in the next question, we're to circle irrational numbers. By the way, why didn't I circle this number right here after this little arrow here as being a rational number? Because it ain't a rational number, right? It has a growing pattern on it. It goes on forever. It's not repetition. It's a growing pattern, so it's irrational. That's why I didn't circle that one in the last problem. However, this one I should be circling, right? Because it is a growing pattern to infinity, all right, never stops. Therefore, it is an irrational number. All right, this is not an irrational number, so don't let me confuse you with that, because it is a what kind of decimal? It's repeating 62, 62, 62, 62, right? All right, if you look at the next one, it is irrational, all right, because of my what? Crazy arrow on the end, right? Okay, look at the next one, real number. There is no number there that isn't real, right? All those numbers are different types of real numbers, okay? So I would circle absolutely all of them, all right? So they're all real. All right, next, the natural numbers. Well, let's see. 0 is not a natural number. You did not learn to count with it. You may have counted up to 75 as a young kid. Can't have negatives. 38, 1526 if you counted that high. 92, 13. Of course, negative 41 is not a natural number because it is negative. And of course, this has a decimal on it, 7.39. No good. All right. And whole numbers. Okay, 0 is a whole number. You circle the rest. You should have circled 16, 296, 598, and 105. The decimals are not whole numbers, okay? And the negatives are not whole numbers. Okay, let's go on. Describe the decimal behavior of an irrational number. Right? They go on forever. They don't repeat. Don't terminate. And do not show a pattern to infinity. Well, let's see. If you place $15 in a large barrel every 10 minutes for the next 27 years, will you have accumulated a sum of at least $20 million in that barrel? Assume there are no leap years and that you have a huge barrel. Show how you determined your answer. Well, I think the way to think of this problem is that we need to get 27 years into what? Into money. So if we start with 27 years using dimensional analysis, what's the next thing down time-wise in terms of years? Well, the simplest thing to do, the best thing to do, is to go to days. And where does years go, if you remember? On the bottom, so it cancels. There are 365 days in every year. Okay? Now what? This would get it into days. I need it in what next? Hours, right? Well, where does the 24 go? Hours have to go on top because I want days to cancel. So for every 1 day, there's 24 hours. Okay, now let me ask you something. Can we take a little shortcut here? If we're going to put $15 in the barrel every 10 minutes, how much money would we be putting in the barrel every hour? Well, every hour, there are 6 10-minute periods in an hour, right? So we could do 6 times 15. So that would be $90 per hour we would put in the barrel, right? So why don't we just use that, take that shortcut. So $90 per every 1 hour go into the barrel. Hours cancel, days have canceled. So if I multiply 27 times 365 times 24 times 90, I should have the answer I'm looking for, correct? So on my calculator down here, I'm going to do 27 times 365 times 24 times 90. Here's the number I get. The number I got was 21286,200. Putting the commas in here, that appears to be $21,286,200. Did I do it? Did I have at least $20 million in the barrel? Absolutely. So as my work shows, I have done it. QED, quite enough done. QED, quite enough done. You've shown it. Well, let's take a look at problem 12. Determine the missing digit in this bank routing number. Remember to use 739, 739, 739. Okay, these are a little more complicated because the numbers are a little larger, but we can handle it. So let's put them down. And let's multiply them out. 63, 3x, 63, 42. I'm going to put this one down here. 15, 36, 21, 6, and 0. So now, this will become a 3. This, of course, stays 3x. 3, 2, 5, 1, 6, and 0. If I add these all together, 3 and 3 are 6, 7, 8, and 5 are 13, 14, and 6 is what? 20. All right. Now, let me make sure I did that right. 6, 7. Oop, wait a minute. I forgot 36 here, didn't I? So for 36, it becomes what? 6 down here. Don't want to forget that. All right. So this is not 61. It's just 6 and 1. So 0, 6, 7, 13, 18, 20, 23, 26. All right, so 0 mod 10 is supposed to come out to be equal to, right? Let's see. What must 3x end in? So when I add it to 26, it ends in a 0. Well, as you can see, it's got to end in a 4, right? Because 26 plus 4 would be 30, or 26 plus 14 would be 40, or 26 plus 24 would be 50, ending in 0, right? All those. So x has to end in a 4. What times 3 ends in a 4? It is x equals 8, right? 8 times 3 is 24. So x equals 8 is the correct answer. So the missing number in the bank routing number is an 8. Finally, the last question. Why can't this number be written or converted to a fraction? This number shown right here is what? Phi, the golden ratio. Remember, the golden ratio, its exact value is 1 plus the square root of 5 all over 2. What kind of number is square root of 5 up here that I'm putting my pencil notifier around here? It's irrational, isn't it? So, therefore, since phi is an irrational number, it cannot be written as a fraction. Okay, now we have completed this review sheet. Please make sure you send it to me so I can give you 10 points for having taken the time to go through it with me and to think about all of these questions. Don't forget, there is also an assignment due. It was given to you in the beginning of the video, okay? So make sure you do the assignment and the video quiz. I believe it's video quiz 13. And please make sure you send that to me as well. Now, there is a short remainder to this video yet, which will be discussing the fact that I have been making some of these videos recently, but I've also made some of the videos before, like last spring, when COVID was at its max. And when COVID was at its max, I was doing them on my laptop, which did not have a very clear camera vision. I'm going to talk about that very briefly. It won't take long, so don't worry. All right, I hope all is well with you, and just watch the remaining part of the video, please, right now. After this next class, which puts together the review, I'm going to again start new material. Now, I do want to say a couple things about this new material. It's going to be quite different than any of the stuff we've just been doing the last several classes. We're going to visit geometry quite a bit. Don't worry, it isn't proofs and all that stuff, but we're going to visit geometry, and we're going to take a look at how the golden ratio comes into play. But one thing I don't particularly like about the beginning of some of these videos that I did, they are the first ones I made once COVID set in. So you're going to see me addressing the topic of COVID quite a bit in some of these videos. Just ignore that because we're kind of by that now. But I want to use the same videos. The only problem with them is that the camera I was using at the time wasn't tremendously clear. All right, it was in my laptop, but I ended up buying new cameras because I was not pleased with the picture. Not that I wanted to look good, I don't mean that. It just kind of looked a little fuzzy. So you're going to see that some of the videos that we're going to work on for the next classes might be, particularly ones I made using my laptop, are going to be a little bit fuzzy. And the COVID comments or whatever I might say in relation to hoping your family is well and all that, you know I mean that, but we were in the midst of the COVID crisis at that time, and a lot of people that I was dealing with when I taught that, finished the spring semesters and used those videos, were living in New York City, and it was crazy down there. So please be patient, don't worry about it. Also, the coding system that I use for the videos all has dates on it, like April 4th, April 10th, April 20th. Just ignore that. I will put those dates in parentheses when I tell you what video to watch. I will classify the videos the way I have been, except when you click on the link, when it comes up, it's going to be the name that's in the parentheses. It's not going to be the name you're used to seeing, which is usually COVID video class such and such. It's going to be the thing that's in parentheses, like the date April 5th or April 20th. So don't be confused by that. Just go to the links. The links will be correct, and you can watch the videos as I teach you the material. So Big Quiz 2 is about to be in your future. We're going to have 2 videos that you're going to watch in the next class. So I will see you for the next class. Please get this homework done for me, and we will definitely be talking soon. And I hope all is well with everyone. Take care. Bye-bye.